All right, well, good morning and happy Friday. Sorry, the text is wrong. It says Wednesday, but it's Friday, okay? Week 4, Friday. And we are looking at just a few more sampling techniques, okay? And so we will look at something called the Box-Muller transform. This is a method to generate values from the normal distribution. Now this is a little bit maybe a little quaint in that it's not used. It's not used in modern kind of when you ask your computer to do R norm and generate random normal values. It uses its own kind of approximation inverse CDF method, and that method is kind of the faster. But this is kind of it's creative and smart, and it can be used to generate random normal variables. And so it's kind of like it's like learning kind of these classical methods and going from there. So I don't know. Do you have to learn how they measured like the speed of light first time with like this spinning mirror, and they, I don't know, kinds of creative little historical solutions for problem solving for these different kinds of things. So that's what we'll look at. This is known as the Box-Muller transform because it's named after these two people. And 1958. So that's what, 66 years old, this method. Okay. But what it will do is it generates, it takes random uniform and it turns them into random normal values, okay? And it accomplishes this by going from kind of a pair of Cartesian coordinates to a pair of polar coordinates. And so it's kind of a neat little trick, okay? So, oops. Okay, so what we're going to do is we're going to say x and y are independent standard normal random variables. So because x and y are independent, we could say the joint density of x and y is the product of the PDF of x and the PDF of y, because they're independent, right? And so this is the PDF for standard normal. So, it's normally what, root 2 pi sigma, but sigma is going to be 1, and then, x minus mu squared, but mu is 0. So it's x squared. And so you have the density of a standard normal x times the density of the standard normal y, and when you do that, you can combine them into this. Okay, so the joint density of two independent x variables x and y will be this. Okay, and then we are going to take a pair of Cartesian coordinates and a pair of polar coordinates. So polar, you measure everywhere on the kind of the plane using the length of your radius and an angle theta, and then x and y is along the x-axis and the y-axis. And you can basically, if you're using real numbers, every single point on the real number plane for x and y real number plane can be turned into a pair of coordinates r and theta. Okay, and so the conversion here is x is r cosine theta, y is r sine theta, and that's what you have. And so we're going to go from a function of x and y, and that will become a function of r and theta. And this is how you would go about doing that to change this. Okay, so it might be a while since you've had to do this, but in multivariate calculus, if you wanted to do a change of variables, you have to do something like this, okay? dx dy over dr d theta, and then this part right here becomes the Jacobian of this thing, okay? And you're going to get dx dr, dx d theta, dy dr, dy d theta, the Jacobian of all of these kind of partial derivatives. And so, you know, dx dr is cosine theta, dx d theta is going to be negative r sine theta, dy dr is sine theta, and dy d theta is r cosine theta, right? So using these relationships and doing this, and then so your Jacobian, when you kind of take the determinant of this thing, you get r cosine squared theta plus r sine squared theta, and that's just going to reduce down to r. Okay, so going from fxy into fr theta, basically we're going to have fr theta is going to be fxy, and then this Jacobian here is going to just be replaced with r. Okay, so that's what we have. Okay, this is just dredging up the what is this, 32b or something? I don't know, something like that. Okay, all right. So we have this. Remember, we had e to the negative x squared plus y squared back here. Okay, e to the negative x squared plus y squared, and we know that x squared plus y squared is r squared. So when we say f of r theta is fxy times r, because this this change of variables part right here, the j, that's r. So our f r theta, our function there, is going to be 1 over 2 pi e to the negative r squared. We replace x squared plus y squared with r squared times r. Okay, and then so for r greater than or equal to 0, so we're assuming we have a positive, you know, our value r can't be negative, and then our angle theta is between 0 and 2 pi. Okay, we're going to have this. Okay, and so fr theta is going to be, fr theta dr d theta is going to just be this exact thing, dr d theta, okay? And applying we're going to do another change of variables, okay? And we're going to go from r to r squared, okay? So going from, if you are going to do a change of variables at dr squared, that's equivalent to 2r dr, okay? So here we're going to replace this r dr right here with 1/2 dr squared here. Okay, so with all of that, this 1 over 2 pi e to the negative r squared over 2 times r dr becomes 1/2 dr squared. Okay, and then we can kind of do some term rearranging of terms. And basically over here, I'll have 1 over 2 pi d theta, and then I'm basically just swapping the constants, okay? From 1 over 2 pi, and then this to be 1/2 here, okay? So now I can factor this, and these are two independent PDFs, okay? So this here is the PDF of a uniform variable that goes from 0 to 2 pi, right? So if you think about, you know, what is the PDF of a uniform variable, if that's equal to 1 over root 2 pi, if it's 1 over 2 pi, if that's the PDF, that's equivalent to that's the PDF of a uniform going from 0 to 2 pi. And then in this part right here, okay, if you have a 1/2 e to the, you know, x over 2 or whatever, y over 2, that's equivalent to an exponential distribution, okay? Exponential distribution with rate parameter 1/2. Okay, rate parameter 1/2. It's just that the random variable is an r squared. Okay. So we've got this is, you know, your variable here, because the PDF is what, lambda e to the negative lambda times x, and so you know your lambda is 1/2, and then your x, the random variable is x or whatever. Here in our case it's r squared, and so r squared comes from an exponential distribution here. Okay, and we have a product of two PDFs, so r squared and theta themselves are independent. Okay, what does that mean then? So what we're going to do is we are going to generate a uniform value, okay, from 0 to 2 pi, which we can do. And then we're going to generate an exponential value, random exponential, with parameter, rate parameter lambda is 1/2, okay? And then once we have a random exponential, which is equal to r squared, we can take r, and that will be the square root of v. And we'll just keep the positive side because we know r has to be positive. Okay, and we can generate these with random uniform values. Okay, random uniform from 0 to 1 is very easy to switch into random uniform from 0 to 2 pi. Just multiply it by a factor of 2 pi. And then random uniform, to go from random uniform 0 to 1 to an exponential, okay, you would use inverse CDF method. And you would say, okay, well, if this is the exponential thing, basically you can just take the log of your uniform random value, and that will be an exponential random variable. Okay, so using inverse CDF method, and so you'll get an r and a theta, and then you can switch, go from r cosine theta and r sine theta into an xy, and so that will, and x and y will be independent from standard normal distribution. Okay, so this is how it's going to go. We're going to generate a random uniform, and then we will get our random theta by multiplying it by 2 pi. We'll generate a random uniform v, and we will get our radius by doing making that random uniform into exponential by doing negative 2 log of that, and then we'll take the square root of that. And then once we have a theta and an r, we will get our x and our y value by doing r cosine theta and r sine theta. And once you do that, then you will have a pair of standard normal independent variables. Okay, so this is kind of a lot here. Let me just kind of demonstrate. So here I'm going to just generate 1,000 values, okay, from the uniform, and we will make thetas by doing 2 pi times these uniform values. I'm going to generate 1,000 random uniform values v, and we will do negative 2 log of v, take the square root, that will generate my r's, and then I'll do r cosine theta and r sine theta, and that will generate x and y. So we'll get 1,000 x's and 1,000 y's. And if I plot all of these, indeed, these look like kind of the product of two standard normal random variables. And I can also run this, and you can see that if you look at the plot of x, let's see if this runs. You look at the plot of x and the plot of y. So here are my x values, and I can do a histogram of x. Okay, and that looks normal. I could do a QQ norm of x, and that very much looks normal. I can do is it Shapiro test on x. Okay, this is a normality test. We get a p-value of 0.56, indicating we don't have evidence to say that it is not normal. Okay, and I can do the same thing for y. My y, that also looks normal. QQ norm of y also looks normal. And Shapiro test of y also gives me a p-value that indicates I don't have any evidence to say that it is not coming from a normal distribution. So that's good, okay? And that comes from U, which is, random uniform, okay? Histogram of V, also random uniform. See, these are random values, and we've converted that. There's kind of a neat little illustration on Wikipedia that shows kind of how it maps. So basically, this what do you call it? This square right here, going from the origin 0, 0 up to this corner 1, 1, corresponds basically every location here in this box, 1 by 1 box, corresponds to a location in the normal distribution. Okay, so if, say, the coordinate you generate has an x value of 1, okay, that corresponds to a radius of 0, okay? Whereas if your x value is like 0.9, okay, or whatever this value is, 0.95, then it corresponds to a kind of a short radius, because we're taking the log of the thing, and then we're taking the square root of that, okay? So negative of the log of the thing, -2 times the log of that. So log of 1 is 0, and then as your values get closer and closer to 0, the log of that becomes more and more negative, right? And we're taking the negative of it, and we're taking the square root. So as my x values get smaller and smaller, you can see the point that it translates to the what do you call it? The radius gets longer and longer, okay? Whereas the y coordinate corresponds to the angle theta, okay? And it's uniform. So if y is 0, my theta is 0, and if y is 0.5, my theta is going to be pi. If my y is like 0.75, it corresponds to 1.5 pi, and when y is 1, my theta is 2 pi. Okay, so you can see if I keep my x constant and I go around, this corresponds to the values here. So this right here, this corresponds to this vertical red line right here. This corresponds to x being equal to e to the -1/2. Okay, and that translates to a radius of 1. Okay, and then yeah, this right here, these are all values that are going to have radiuses less than 1, and then these will all have values with radiuses greater than 1. Okay, and then this corresponds to the angles. And so when you kind of map all of these out, every single one of these points translates to a point on the in the kind of the normal circle there, right? And so you're going from a pair of Cartesian coordinates to kind of a pair of polar coordinates, and then the distribution of everything follows a normal distribution for y and x after you kind of translate everything. So this is kind of, I think it's kind of a neat thing. All right, so this is a creative solution for dealing with trying to generate random normal values. Okay, it turns out that we don't use this method today because the computations involved with taking the log and taking these trig functions, cosine and sine, it takes the computer a several cycles to calculate these values. Okay, so we have functions in the computer that can do this, but it's relatively computationally expensive versus just like calculating a polynomial. Okay, and so our normal approximation CDF, normal CDF that we use for the inverse CDF, that one just is able to calculate the values even faster. So that has overtaken this. But that's the Box-Muller transform, kind of a creative solution for dealing with trying to generate random normal values. Okay, let me give you your first view quiz answer. Sorry. Okay, I got logged out. All right. Well, let me keep talking while I'm logging in over here. Okay. So now that we can generate values from the standard normal distribution, okay, either from using the Box-Muller or just assuming we have access to a computer that can do our norm, okay, we might say, well, how do I go from a standard normal to some arbitrary normal distribution, okay, where I have a different mu and a different variance. Okay. Well, basically, you just take your z's and then you just kind of add a constant or multiply it by a constant. Okay. All right. Let me give you your Friday view quiz answer. The first one is the letter A. A as an apple. A as an apple. So if you want to go from standard normal with a mean of 0 to a normal distribution with a mean of mu, you just add mu, okay? And then whatever your z is, if you want to have a standard deviation of sigma, or variance sigma squared, you just multiply that resulting z by sigma. And if you do that, okay, and you generate w by doing basically sigma times z plus whatever mean mu you have, the resulting random variable w will also be normally distributed, and it will have a mean of mu, and it will have a variance of sigma squared. Okay, so going from standard normal to arbitrary normal is very simple. You just basically you're like doing the undoing the conversion to a z-score. So you're multiplying by sigma and then adding mu. Okay. If you want to, sometimes we want to generate samples like a multivariate sample. Okay, and I'll start with like the discrete case, and then we'll do a multivariate normal, and then we'll kind of leave it at that, right? So higher dimensional random variables or pairs of random variables and higher dimensions, you could have all kinds of complicated probability structures. Here we'll just start off with a simple one where we have a discrete distribution, okay? Eventually we'll want to get to higher dimensional distributions, and we have future tools like Gibbs sampling to generate samples from that, but we have to kind of work our way up to it by talking about Markov chains and whatnot. But let's say we want to generate a pair of values, x and y, okay? But x and y are not independent, okay? The distribution of y, basically, and x, it's not just a product. You can't just take x and y, because x being 0 and y being 1 has kind of the most probable thing of 0.6, okay? But then, so when x is 0, y is more likely to be 1 than it is to be 0. So 0.6 versus 0.2. But when an x is 1, there's basically the probability that y is 1 or y is 0 is the same, right? It's like 50-50 when x is 1, but when x is 0, y is much more likely to be 1. So these things are not independent, and how are we going to generate samples from a distribution like this? Okay, well, the trick is basically just to kind of map all of these probabilities, okay, onto the real number line from 0 to 1, okay? And so it's just kind of arbitrarily, we will order them we'll take the top left corner of point 2 and we'll map that from 0 to point 2, okay? And then the next value, point 1 here, okay, x1, so we'll kind of go down like this. We'll get mapped from point 2 to point 3, and then the next value of point 6 will get mapped from point 3 to point 9, and then finally that last corner will get mapped to point 9 to 1, okay? And so we're just, so you have x and you have y, okay? 0, 1, 0, 1. This is point 2, point 1, point 6, and point 1 here. And we're just going to try to map it from 0 to 1. And so this part will go right here. Right, so this will correspond to 0, 0. And then this next part, point 1, will correspond to right here. And so this will be 1, 0. And then here we have point 6. So that will go from here to here. So from here to here will be 0, 1. And then right here will be 1, 1. Okay? And so it's just kind of an arbitrary ordering of these things. You know, if somebody wanted to say point 2 to point 8 is going to correspond to 0, 1, that would also just be equally valid. Okay, so it's just an arbitrary ordering of the different cells in here onto the real number line from 0 to 1. Okay, and then so now you'll just generate a random value from the uniform distribution, and then based on these cutoffs that we've produced, you'll generate your x and y coordinates. Okay, so how do you generalize something like this into, say, something even bigger? Okay, so what if you have a more complicated thing where you have x can take on 4 values, y can take on 4 values, and or just kind of more generally speaking. Okay, so again, you just kind of go down the column. All right, so again, an arbitrary ordering, but we'll say 0 to 0.02 will correspond to 1, 1. And then the next value is 0.03, so 0.02 to 0.05 will correspond to 2, 1. And then 0.05 to 0.09 will correspond to 3, 1, so on and so forth. And you keep going until you get to the end where values from 0.9 to 1.0 will correspond to 4, 4. And so, you kind of have to map everything out there, okay? Going from, whatever these, you have to calculate all of these kind of cutoffs, okay? F1, F2, F3, F16, and so on and so forth. So how would you go about doing this, okay? So here I've got a matrix. This is my 4x4 matrix that corresponds to all of this. 0.02, 0.03, 0.04, 0.01. Okay, so I've got all of those, 0.02, 0.03, 0.04, 0.01. Okay, and then what we will do is we'll make a vector of cumulative probabilities. Okay, so this is basically going to be all of these F1, F2, F3, up through F16. Okay, so basically all of these will correspond to the different cutoffs. And so, if a value is between 0 and 0.02, it'll correspond to 1, 1. This will correspond to between 0.02 and 0.05 will correspond to 2, 1, so on and so forth, until we get to between 0.9 and 1.0, and that will correspond to 4, 4. Okay, so this is what we have. And then what we need to do is we need to map all of these things into basically what the x and y values are going to be. So, we're going to, basically I'm going to just create a vector x values that go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then y values, I'm going to repeat each one 1, 1, 1, 1, 2, 2, 2, 2, and so this kind of corresponds to all of these things. Okay, so this is my vector of cumulative probabilities, and so if I generate a random u that's between 0 and 0.02, it'll correspond to x being 1 and y being 1. If I generate a value between 0.02 and 0.05, that will correspond to x being 2 and y 1. So these are the different values that I get. And then what we want to do is we're going to generate a random u. So let's say I generate my random u, and my random u is 0.01. Okay? I want to ask which cumulative probability, okay, is greater than u, okay, but I want the smallest one that's greater than u, okay? So the smallest value of u, smallest cumulative probability that's bigger than 0.01 is going to be the first one, okay? 0.02 is the smallest one, so that will correspond to the first one, and now I will pull out the x and the y that correspond to the first value, which will be 1 and 1, okay? Let's say I generate a random value of 0.03, okay? 0.03 is between 0.02 and 0.05, so I ask which cumulative probability is greater than u. So it's going to be true for all of these values, 0.05 and everything to the right of that, but we're going to say which one's the smallest, okay? The second one, okay, 0.05. And then I'm going to get the value of x and y that corresponds to that second column, okay? And then so, here is 0.89. I say, hey, which one's the smallest value that's greater than 0.89? That would be like 0.9, okay? This is the smallest one that's greater than that, and that would correspond to 3 and 4, right? And so you can see how it kind of corresponds to the process that we want. So, this requires you to have kind of the table of, your discrete multivariate distribution of all of these things. And so, so we can do this. We'll generate a whole bunch of these values. I'll generate 10,000 of these things for random values of u, okay? And then what I'm going to do is I'm going to just kind of get the position, which is going to be, hey, which value of u, or which cumulative probability is greater than u, and then we'll calculate that for everything, and then and we will extract all of the x values and all of the y values. And I'll create a data frame of all of those x and y values. And so this is the resulting plot of everything, which, what is this? This is values of 2 and 3, x, 1, 1. So what, 3, 2, is that the highest probability? I didn't even notice. Yeah, 3, 2. It got plotted, this is 1, 1 is in the top left corner, but then in the plot, 1, 1's in the lower left corner, so it looks a little bit funny. But this one has the highest probability of around 0.2. The other ones have, probabilities of, say, these are 0.1 each, and these ones have lower probabilities of like 0.01 and things like that. Okay, so so that's how we would go about generating something from a discrete distribution, multivariate discrete distribution. If you want, it's just kind of a mapping of everything here to the real number line, 0 to 1. Okay, let me give you your second view quiz answer, which is the letter B. B as in bear. Okay, and then finally, we'll talk about generating values from a bivariate normal distribution. And for this, I'm going to just use Professor Tsang's notes because he did a good job, and I was just going to, it would have just ended up with me just kind of copying his notes. But the idea here is now you have a normal distribution, and you're generating x1 and x2, okay? And this comes from a normal distribution, but there's covariance between variables x1 and x2, okay? So x by itself is normally distributed, x1 by itself is normally distributed, x2 by itself is also normally distributed, okay? With mean mu1 and variance sigma 1 squared, and x2 has mean mu2 and variance sigma 2 squared, okay? But x1 and x2 has covariance in that you have this covariance matrix where you have covariance sigma 1, 2 between x1 and x2, okay? So, the definition of covariance is basically the product, the expected value of the product of x1 minus mu1 and x2 minus mu2. So basically, if you have positive covariance, that just means in general, when x is greater than average, y is also going to be greater than average. And if x is less than average, y is also less than average. That's positive covariance, and then negative is just the opposite. When x is above average, y is below average. When x is below average, y is above average, right? So it's kind of the overall, what's the expected value when you look at, is x greater than its mean? Is x2 also greater than its mean, or is it less than its mean, so on and so forth, okay? Obviously, there's random variation, so sometimes an individual value might be greater or less than the mean and go against the trend, but overall, what's the expected value? When you're comparing a value against its mean, is it above or below the mean? Is x2 above or below the mean? And do they vary, right? When there's no covariance, that basically means when x is above or below the mean, okay, the expected value of x2 is going to be at the mean, so you have no covariance, okay, because whatever x1 is, it's not telling us anything about x2. Same thing, zero covariance would be, if x2 is above the mean, x1 might be above or below the mean. The expected value there would be around 0. The product of these things would be 0, okay? All right, so anyway, this is what we want to do. We want to figure out how do we go from kind of independent normal variables or whatever, can I turn them into a pair of normal values that have covariance between them? How do I generate something like that? Okay, so we're going to make this vector mu that basically is the mean of x1 and the mean of x2, mu1 and mu2, and we also need to somehow create this matrix. We want this resulting covariance matrix to be sigma, this thing, sigma 1 squared, sigma 1, 2, sigma 2 squared, okay? What we're going to try to do is we're going to say, well, can we make up some matrix A, okay? And we're going to suppose that when I multiply A times x1 and x2, okay, the resulting result there is going to be y, and that this thing y is going to have this distribution, okay? Y is going to come from a bivariate normal distribution where the mean is mu and the variance covariance matrix is sigma, okay? And so that mean vector of y is going to be basically A times mu, and then the variance matrix, the variance covariance matrix, if you kind of follow the process, it'll be A sigma A transpose, right? It's kind of like when you multiply a variance or a random variable by a constant, the variance is that constant squared. Like if you have variance sigma squared and you multiply the random variable by A, you would get A squared sigma squared for your variance. And it's kind of like that, but it's the linear algebra version of multiplying by a square, and you get A times the matrix A transpose. Okay, so can I use values from the standard normal? Okay, standard normal distribution centered at 0, variance 1. Okay, to get samples from the bivariate normal. That's what we want to do. Okay, so what we're going to do is we're going to just start off by just generating random values of z from the standard normal distribution. We're going to assume we can do this. either from using our norm on our computer, or we could use the Box-Muller transform if you're stuck with using random uniform or something like that, okay? So my pair of z values, okay, is normally distributed. Well, I got two independent z values, z1 and z2, and if I kind of put them together into a joint distribution, all right, basically I'm going to have this vector z where the mean is 0, and the variance covariance matrix is basically the identity matrix, okay? Z1 has variance 1, Z2 has variance 1, and there's no covariance between them. So basically we're getting the equivalent of this, okay? So we're going to generate pairs of points, and we're going to get basically Z1 and Z2, and if I plotted them all, it would look something like this. Okay, and we're going to say, all right, well, what we're going to do is we want to figure out some matrix A and some vector B, so that when I do take this pair of points Z and I multiply it by matrix A and I add vector B, the result is going to be a vector X, where X comes from this bivariate normal distribution with mean mu sub X and variance matrix sigma X, okay? So this is what we want to do, and the answer and the question is, well, can we figure what these things are, right? So the mean is pretty simple, okay? We would just whatever z's are, okay, they're centered at 0, but we would just basically add our vector b, okay? Our vector b is going to basically the mean of the desired distribution. So if you're if you want a mean of 3 and 2, okay, then you'll just add 3 and 2 to whatever your values are. Because if you take x and you say, well, I'm going to just add some vector b, or after I take z and multiply by a, well, the expected value of z is just going to be 0, right? So if I do 8 times the expected value of z, that's just going to be 0. So what is the mu that I should add? Well, what is the b that I should add? It should just be equal to the desired mu. All right, so if we set b equal to this, then the resulting distribution of x will have that desired mean. All right, what about the matrix A? Okay, so remember what we want, okay, is we want to take z, multiply it by a, add a b to it, so that we're going to define our x like this, and we want to figure out what the a is, so that the resulting covariance is going to be this target matrix, okay? The desired covariance matrix that we want. Okay, so we're going to say x is defined by doing a times z plus b. And what is the covariance of that? Well, the covariance of that, if you're just adding a constant b, the covariance is just going to be a times z. And anytime you're calculating the covariance of a matrix times z, and you want to pull it out of there, you're going to get a covariance z a transpose. The covariance of z itself is just the identity matrix, okay? It's just 1, 0, 0, 1. So therefore, the covariance of x will be a transpose. So what we want, if this is the desired covariance, sigma x, that whatever arbitrary matrix we've decided, what we need to do is we need to figure out a matrix A, so that a transpose is equal to this desired matrix sigma x. Okay, so we want to find a matrix A so that a transpose is equal to whatever matrix we want. And how do we do that? Well, we have a thing called the Cholesky decomposition. Okay, in the Cholesky decomposition, we say, if you have some symmetric positive definite matrix sigma, okay, so basically, your variance covariance matrices are going to be symmetric positive definite, unless your variance matrix is all zeros. Okay, well then it fails. But everything else, it will be a positive definite matrix. we're going to say, okay, we can figure out a lower triangular matrix such that AA transpose is equal to that matrix sigma, okay? And that's the Cholesky decomposition. You can just, your computer can just do this. You can just say Cholesky, I think. I forget what the actual function name is. But we can also do a little bit of math ourselves to figure it out. So we're going to say A is this lower triangular matrix with these terms. The top right value is going to be 0. So we're going to call this T11, T21, and T22. And then we want to figure out what it should be, AA transpose, so that it is equal to the desired matrix sigma, okay, which has terms sigma 1 squared, sigma 1, 2, sigma 1, 2, sigma 2 squared, okay? And so if you do all of this, you'll have a system of equations, okay? So if you do AA transpose, you'll get this. And basically, you'll have 3 equations and 3 unknowns, okay? You have a T11, a T21, a T22, and you have sigma, so T11 squared is equal to sigma 1 squared. So T11 is going to be equal to sigma 1. And then you have, you know, this equation T11 and T21 is equal to sigma 1, 2. So you can say, well, T21 is equal to sigma 1, 2 divided by T11, okay? And then the last one is you have T21 squared and T22 squared is equal to sigma 2 squared. And so just kind of solving for that, 3 equations, 3 unknowns, you'll get, this is the solution that you arrive at, okay, for what this thing is. Okay, so if you use this, then the result will end up, you will end up with this matrix A that you can then use to produce your matrix X. So you'll generate random values from standard normal distribution centered at 0 with covariance 1, okay, independent. Z1 and Z2 are independent of each other. And then you multiply it by your Z1, Z2 by that matrix A. After you figured out those terms, you'll add on whatever vector of means to it, and then that will give you your random variable X, and X will have this distribution where the mean is mu and the variance covariance matrix is sigma. All right, and so to demonstrate this, okay, so this is just saying all of that, we can say, all right, I want to generate 1,000 values, and I want to create, random variables X, okay, where the mean is going to be 1, 2, okay, centered at the coordinates 1, 2, and then we'll just we'll have covariance of 0.7. Okay, so I want to have some positive covariance between x1 and x2. The variance of x1 is 1, and the variance of x2 will just be 1, but we have covariance between these two things. Okay. So I'm going to generate a bunch of z values. I'm going to generate basically 1,000 z1 and 1,000 z2 values, arrange them into a matrix of 2 rows and 1,000 columns. Okay, so I've got this big matrix Z. All right, and then yeah, there's a function Cholesky that we can do to figure out what this matrix, what the values of A are. Okay, I guess R does, when you do Cholesky, it gives you the upper triangular matrix. So if you want the lower triangular matrix, you would just take the transpose of that. Okay, so you can just do Cholesky sigma, or you could do it yourself with these terms. You'll get the same results. Okay, and then and what we'll do is we'll do A times Z plus mu. Mu plus A times Z is going to be my X. And if we do that, then the result is indeed bivariate normal. Okay, so we're basically going from something like this, where you have 2 independent normal variables, and they get kind of translated into something like this, where you get a bivariate normal where there's covariance between the terms. Okay, and that can be useful in terms of generating, certain values, certain things in like if you look at height and arm span. Okay, there's high covariance between them, right? Generally, taller people have longer arm spans, but you also have, certain people will have relatively short arms. Certain people have relatively long arms, right? You think about certain basketball players, and basketball players are just generally really tall, but also some of them have like really long arm spans. So you might have, what do you call high positive residual, or low negative residual or something. Okay, anyway, that is generating values from the bivariate normal. Okay, we will go ahead and wrap things up here. Let me give you your last view quiz answer. Last view quiz answer today is the letter B. B as in bear. Okay, have a great rest of your day and a great weekend. We'll see you next week.